What if the hardest jolt to hit New Zealand's North Island in years came from a fault that almost nobody talks about, sitting directly beneath a sleeping supervolcano? At 4:51 in the morning, the ground dropped, houses shuttered, and people from Auckland to Gisborne woke up asking the exact same terrified question. Was that the volcano finally moving? The real answer is stranger and far more interesting than any headline you've seen, because the fault that shook those people awake and the fault that could genuinely devastate this country are not the same fault at all. Before we go any further, do me one small favor. If you prefer explanations that treat you like an intelligent adult instead of scaring you for clicks, tap that like button right now, subscribe so you don't miss the follow-up when new data comes in, and share this with the one person you know who panics every single time the Earth moves. 3 seconds of your time decides whether accurate science reaches more people than fear does. Let's start with what actually happened, in order. Because the sequence matters more than most coverage admits. It began in the middle of the day. A magnitude 5.7 earthquake ruptured roughly 49 kilometers west of Hatepe, deep inside the central North Island, at a depth of about 10 kilometers. On its own, that's already a serious event. A shallow 5.7 is not background noise. It's the kind of shaking that rattles windows hard, knocks unsecured shelves over, and sends people ducking under tables. Emergency services logged calls. Social media lit up. Most people assumed that was the story, and that the ground would settle back into silence the way it usually does. It didn't. Less than 24 hours later, in the pitch dark of early morning, a second and stronger earthquake struck. Magnitude 5.9, centered near Taumarunui, only about 20 kilometers from the first rupture, and this time even shallower, just 9 kilometers below the surface. That's genuinely shallow for this part of New Zealand, and it's the single most important number in this entire story. People felt it in Auckland, hundreds of kilometers north. They felt it in Wellington to the south, in Napier and Gisborne to the east. Thousands have felt it. Reports flooded in within minutes. In the towns closest to the epicenter, residents described being thrown awake by what sounded like a truck slamming into the side of the house. And here's where the fear kicked in, because of where this happened. Both of those epicenters sit on the edge of the Taupō Volcanic Zone. Not near it, not in the general neighborhood of it, right on the rim of one of the most restless volcanic regions on the planet. So, when the phones started buzzing at 5 in the morning, the question was really about earthquakes at all. People weren't asking how strong it was. They were asking whether the ground under Lake Taupō had finally started to move again. And that's a fair question to ask, because of what's buried under that lake. Lake Taupō is not a lake in the way most people picture one. It's a wound, a hole in the earth left behind by one of the most violent volcanic systems humanity has any record of. The lake fills a caldera, a collapse crater formed when a magma chamber emptied itself so catastrophically that the roof of the earth above it caved in. Around 25,500 years ago, this system produced the Oruanui eruption, one of the largest eruptions of the last 100,000 years anywhere on Earth. It buried the central North Island under ash and pumice hundreds of meters thick and rewrote the entire landscape. That is what supervolcano actually means. Not a bigger version of a normal volcano, but a fundamentally different kind of event. And it didn't stop there. Around 1700 years ago, in an eruption geologists call the Hatepe event, Taupo erupted again. Not a super eruption this time, but still one of the most violent eruptions of the last 5,000 years. It flattened forests across enormous distances with a pyroclastic flow that moved at hundreds of kilometers an hour. In geological terms, 1,700 years is not history. It's the day before yesterday. So when a magnitude 5.9 earthquake goes off on the edge of that system, the fear is not irrational, it's earned. The question is whether the fear matches what the data actually shows, and that's what the rest of this video is going to answer properly. To understand that, you have to understand why this specific stretch of New Zealand is so violent in the first place. Underneath the eastern side of the North Island, the Pacific tectonic plate is diving down beneath the Australian plate. That's a subduction zone, and it's the engine driving nearly everything geological in this country. But subduction doesn't just push, it drags. As that dense oceanic slab sinks, it pulls at the crust sitting above it, and the crust responds the way anything responds. To a steady pull, it stretches, it thins, it cracks. And that's exactly what the Taupō Volcanic Zone is. Not primarily a chain of volcanoes, but a continental rift, a place where a landmass is slowly being torn apart from the inside. That stretching happens at up to around 15 millimeters a year. 15 millimeters sounds like nothing. It's the width of your fingernail. But run it for 100,000 years and you've pulled the crust apart by 1.5 kilometers. Run it for 1,000,000 years and the numbers become absurd. That relentless stretching thins the crust until it's unusually thin and unusually hot, And thin, hot crust does two things. It breaks easily, producing shallow earthquakes, and it gives molten rock an easier path upward, producing volcanoes. Earthquakes and eruptions in this region are not two separate hazards that happen to share a postcode. They're two symptoms of one single process, which is why the fear after a quake like this is so understandable and so easy to get wrong. So how do scientists actually tell the difference? Because here's the thing. There are two completely different ways to shake the ground near a volcano, and they leave completely different fingerprints. The first is genuine volcanic unrest. When magma pushes upward, it cracks rock in a very particular way. You get swarms. Dozens or hundreds of small, very shallow earthquakes clustered tightly together, often getting more frequent over hours or days. You also get harmonic tremor, a strange, sustained humming signal that looks nothing like a normal earthquake trace. It looks more like a vibration than a snap, because it's caused by fluid and gas forcing their way through cracks. Volcanoes are noisy in a messy, continuous way. The second way is a plain tectonic earthquake, rock under stress finally reaching its breaking point and slipping along a fault. That produces one sharp rupture, a clean signal, and a decaying series of aftershocks. No hum, no swarm building over days, just a break. And seismologists have a tool that separates these two possibilities almost immediately. It's called a moment tensor solution, though most people know it by its nickname, the beach ball diagram, because of the two-tone circular plot it produces. When an earthquake happens, seismometers all over the world record the direction the ground first moved. Up in some places, down in others, in a pattern that depends entirely on how the fault slipped. Feed those readings into the maths, and you get a diagram that tells you the geometry of the rupture, whether the fault slid sideways, was shoved upward, or dropped downward. You also get a number describing how clean the break was, called the double couple percentage. A high double couple value means simple, ordinary rock fracturing along a fault plane. A low one, with a lot of what's called an isotropic component, suggests something inflating or deflating underground, which is the kind of signal that makes volcanologists sit up straight. For this earthquake sequence, the solution came back with a high double couple percentage, textbook rock breaking, not magma moving, and it got more specific than that. GeoNet, New Zealand's official geological hazard monitoring agency, described the mechanism as normal faulting, caused by extension of the crust in the upper part of the Australian plate at the edge of the Taupō Volcanic Zone. In plain language, the ground was being pulled apart. A block of crust lost its grip, and it dropped. The rake values, which describe the direction of slip along the fault, came back strongly negative, which is the mathematical signature of extension rather than compression. This is exactly what a rift earthquake looks like, not a volcano clearing its throat. A continent being stretched a fraction of a millimeter further apart, and one tired block of rock finally giving way. Picture it physically for a second, because the mechanics are simple once you see them. Imagine a slab of stone being slowly pulled from both ends. It resists for a long time, because friction along the cracks inside it is holding everything locked. Then one crack loses, a wedge. A rock slides down along an angled surface, dropping a few tens of centimeters in less than a second. That drop releases decades or centuries of accumulated strain in one violent instant, and that energy radiates outward as seismic waves. That's a normal fault earthquake. It's the same process that has built the entire landscape of this region over millions of years, one sudden drop at a time. Quick pause here, because you've made it through the hardest part of the science, and you deserve to know why it matters. If this explanation has already given you something the news didn't, hit like right. Now, while you're thinking about it, because that single tap is what pushes this video in front of someone who's currently reading a panic post about a supervolcano awakening, you've got the actual mechanism. Pass it on. There's another piece of evidence that supports the tectonic explanation, and it's the quiet kind that never makes headlines. New Zealand's volcanic alert levels for the Taupō system did not change. Taupo has genuinely stirred in recent years, so scientists know exactly what that looks like. In 2022, a swarm of earthquakes beneath the lake itself, including a magnitude 5.7, pushed Taupo's volcanic alert level up to level 1 for the first time since monitoring began. That was accompanied by measurable ground deformation, the lake floor literally rising, which is the classic signature of pressure changing at depth. That episode eventually settled back down without an eruption, but it proved the monitoring works, and it gave everyone a clear reference point for what real volcanic unrest looks like. This sequence didn't match it. Now let's talk about that depth number I told you to hold on to, because it explains something people found genuinely confusing. Many residents said this quake felt worse than earthquakes they remembered being larger. That's not imagination, that's physics. Most of the big earthquakes under this part of the North Island happen deep inside the sinking Pacific slab, sometimes more than 200 kilometers underground. In October 2018, a magnitude 6.2 struck only about 20 kilometers from this latest event. On paper, it was significantly more powerful, but it ruptured 207 kilometers below the surface. By the time that energy climbed all the way up through rock, it had spread across an enormous area and lost much of its punch. This one ruptured at 9 kilometers. 9. The energy had almost no distance to travel and almost nothing to weaken it. It went nearly straight up and hit the surface, concentrated and sharp. That's why a magnitude 5.9 could feel more violent than a magnitude 6.2, and why people who slept through the 2018 event were thrown awake by this one. Magnitude tells you how much energy was released. Depth tells you how much of that energy actually reaches your bedroom floor. Any headline that quotes only the magnitude is giving you half of the equation, and usually the less useful half. Here's a way to feel the difference rather than just understand it. Imagine someone knocking hard on your front door. Now imagine that same person knocking with the same force, but from 3 floors below through concrete. Identical effort. Completely different experience. The strength of the knock never changed. What changed is everything the sound had to pass through before it reached you. Deep earthquakes are knocking from 3 floors down. Shallow earthquakes are knocking directly on your wall. And a shallow rupture at 4:51 in the morning, arriving with no warning while your brain is still asleep, is about the rudest awakening geology can offer. The practical results were about what you'd expect from a shallow quake in a rural region. Shaking intensity was strong near the epicenter and moderate to light across a huge stretch of the North Island. There were reports of items thrown from shelves, cracked plaster, and objects falling in homes and shops close to Taumarunui. Roads through steep hill country in that part of the country are always vulnerable, and shallow shaking there raises the risk of slips and rockfalls, especially if the ground is already wet. But the region is sparsely populated, and New Zealand's building standards are among the strictest on Earth for a reason. There was no widespread structural failure. That's not luck. That's decades of engineering built on hard-earned experience. The other thing to expect is aftershocks, and this is where people often frighten themselves unnecessarily. After magnitude 5.9, the crust around the rupture has been rearranged. Stress that was sitting on one part of the fault has been shoved onto neighboring parts, and those neighbors will adjust. That means a run of smaller quakes over the following days and weeks, most of them too small to feel, some of them sharp enough to be alarming. That's not the situation getting worse. That's the situation resolving itself. Aftershock sequences decay in a fairly predictable way over time. The absence of aftershocks would actually be the stranger result. But there's a third thread running through this story, and most coverage ignores it completely. While the central North Island was rattling, a separate string of earthquakes had been firing offshore for over a week along the Kermadec Trench. That's the subduction zone running north from New Zealand, toward Tonga, where the Pacific plate plunges beneath the Australian plate. Multiple magnitude 5 events, some larger, none of them widely felt on land because they're hundreds of kilometers out to sea. To most New Zealanders, they simply didn't happen. And yet, in terms of raw destructive potential, that trench dwarfs the fault that shook Taumarunui awake. The Kermadec Trench is not a minor feature. At its southern end, the two plates converge at around 60 millimeters a year, and further north toward Tonga, that rate climbs to roughly 90 millimeters a year. That's nearly 9 centimeters of plate being consumed annually, making it one of the fastest converging subduction zones anywhere on Earth. Faster than Cascadia off the coast of Oregon and Washington, comparable to the most energetic boundaries off Japan. Faster plate motion means faster strain accumulation, which means more earthquakes, more often. This is a boundary that has produced magnitude 7 and even magnitude 8 class events repeatedly through recorded history. So, is that offshore swarm a warning sign? Here's the honest answer, and it's a little uncomfortable in both directions. A week with several magnitude 5 earthquakes along the Kermadec Trench is close to normal. That boundary is almost never quiet. Treating it as an alarm would be like treating rain in a rainforest as a weather emergency. But normal doesn't mean harmless. It means the boundary is alive, continuously loaded, and fully capable of producing something enormous with no obvious warning. Both of those statements are true at the same time, and holding both in your head at once is the difference between understanding seismic risk and being manipulated by it. Let's take a breath here, because we're about to get to the part that actually matters most. If you found this useful so far, leave a comment telling me where you're watching from, and whether you've ever felt a real earthquake. I read those comments, and they genuinely shape which regions I cover next. And if you haven't subscribed yet, now's the moment, because what comes next changes how you'll read every earthquake headline about New Zealand for the rest of your life. Here's the tension sitting at the center of this whole story. The earthquakes that shook people awake, that made the news, that had everyone talking about a supervolcano, came from a relatively modest, shallow rift fault in the middle of the North Island. Meanwhile, the faults genuinely capable of causing a national catastrophe were doing nothing newsworthy at all. The danger and the shaking are not in the same place. They almost never are. And that mismatch is the single biggest reason public understanding of earthquake risk goes so badly wrong. We fear what we feel. Geology does care what we feel. So let's talk about the faults that actually keep New Zealand's scientists awake at night. The first is the Hikurangi subduction zone, running just off the east coast of the North Island. This is New Zealand's own megathrust, the interface where the Pacific plate grinds beneath the country. It is capable of a magnitude 8 or larger earthquake. Not a shallow crustal quake affecting one district, but a rupture hundreds of kilometers long, shaking that lasts for minutes rather than seconds, and a tsunami generated directly offshore. Cities like Napier, Gisborne, and Wellington sit uncomfortably close to it. This is not a theoretical hazard. Geological records show it has ruptured in the past, and it will rupture again. What makes Hikurangi especially serious is the timing problem. Because the fault runs so close to shore, a tsunami generated by a major rupture could reach the nearest coastal communities in well under 20 minutes. In some scenarios, closer to 10. There's no time for an official warning to be issued, received, and acted upon. That's why New Zealand's public messaging for coastal areas is deliberately blunt. Long or strong, get gone. If the shaking lasts more than a minute or is strong enough that you struggle to stand, you don't wait for a siren or an alert on your phone. You move to high ground immediately. That single sentence has probably saved more future lives than any piece of technology. Hikurangi does something else fascinating that scientists have only understood in recent decades. Parts of it experience slow slip events, sometimes called silent earthquakes. The fault slides several centimeters over days or weeks without producing shaking anyone can feel. It's a genuine earthquake released in slow motion. These events release some accumulated strain quietly, but they also transfer stress onto neighboring lock sections. Researchers monitor them closely with GPS networks and seabed instruments because understanding how slow slip interacts with the locked parts of the fault is one of the most important open questions in earthquake science today. New Zealand happens to be one of the best natural laboratories on Earth for studying it. The second fault is the Alpine Fault, and this one is remarkable for a completely different reason. It slices for hundreds of kilometers along the spine of the South Island, a clean scar visible from the air, where the Pacific and Australian plates slide past each other. What makes it extraordinary is its regularity. By digging trenches across the fault and analyzing layers of disturbed sediment and buried forest, geologists have reconstructed its rupture history going back thousands of years. It breaks in a major earthquake roughly every 300 years on average, not approximately, not vaguely, with a consistency that's genuinely rare in earthquake science and slightly unnerving to look at on a chart. The last major rupture of the Alpine Fault was in 1717. That was more than 3 centuries ago, which means the fault has now been storing strain for longer than its average interval between ruptures. Recent research places the probability of a major Alpine Fault earthquake within the next 50 years at around 75%, with a strong likelihood that it will be magnitude 8 or greater. That is among the highest calculated rupture probabilities for any fault studied anywhere on the planet. Scientists have even drilled directly into the fault zone to sample the rock and measure temperature and pressure conditions at depth. Few faults on Earth have been examined this intimately, which is precisely why the confidence in those numbers is so unusually high. So is the big one coming? Over a long enough time scale, yes. Not as a prediction tied to this week's magnitude 5.9. Not because of an offshore swarm. Simply because New Zealand sits directly on an active plate boundary, and that is what active plate boundaries do. The country exists because of these forces. The Southern Alps are being pushed up by the Alpine Fault. The volcanic plateau exists because of subduction. The scenery people travel across the world to photograph is the visible result of the exact same processes that will eventually produce a devastating earthquake. You cannot have one without the other. That's the bargain built into the land itself. But here's the part that should genuinely give you some comfort, and it's not a platitude. New Zealand is among the best prepared countries on Earth for exactly this. The science is public. GeoNet publishes earthquake data within minutes, openly, for anyone to see, including the moment tensor solutions we talked about earlier. Building codes are strict and have been repeatedly strengthened after hard lessons, most painfully after Christchurch in 2011. Schools run earthquake drills. Coastal communities know their evacuation routes. Ordinary people can tell you the name of the fault nearest their home. That level of public seismic literacy is genuinely rare, and it saves lives in a way no amount of panic ever has. If you've read this far into a topic most people scroll past, you're clearly not the type who settles for surface-level answers. So do the one thing that helps most. Share this video with someone who lives in an earthquake zone anywhere in the world. Not to frighten them, to make sure they know which threat is real and which is noise. That's worth more than 100 views from people who forget it by lunchtime. The contrast with some other regions is stark. Japan sits on comparably dangerous boundaries and has invested enormously in engineering early warning, systems, and public education, and it shows every time a major quake strikes there. But look at the Cascadia subduction zone running along the coast of the Pacific Northwest in the United States and Canada. It's capable of a magnitude 9. It last ruptured in the year 1700, sending a tsunami all the way across the Pacific to Japan, which is how we know the exact date. And yet large numbers of people living directly above it still don't fully grasp what they're sitting on, and a great many older buildings there have never been retrofitted. Awareness is not a soft factor. It's infrastructure, which brings me to the part of this story that I think matters most, and it has nothing to do with rocks. It's about attention. A shallow magnitude 5.9 near a supervolcano generates enormous coverage because hundreds of thousands of people physically felt it, and because the word supervolcano is irresistible. Meanwhile, the Hikurangi megathrust sits offshore, silent, loading up strain, and generates almost no coverage at all because nobody has felt it in living memory. The Alpine Fault has been quietly accumulating 300 years of strain, and it makes headlines maybe once a year. Our sense of danger is calibrated to sensation, not to consequence. And that is a genuinely dangerous way for a species to assess risk. There's one more honest note to end the science on. Saying this earthquake was tectonic and not volcanic is completely true, but it doesn't mean the two are strangers. In a rift zone, faulting and volcanism are cousins. The same stretching that snapped this fault is, over thousands of years, the same stretching that thins the crust and opens the pathways magma eventually uses. This particular event was not magma moving, but it is a reminder that the whole region is under active tension, that the ground there is being pulled apart right now as you watch this, and that the machinery which built Lake Taupō has never switched off. It's just working on a timescale that makes human attention spans look absurd. So here's where all of this leaves us. Two separate fault systems were active in the same week. One shallow, sharp, and beneath the edge of a supervolcano, confirmed by moment tensor analysis and by GeoNet as ordinary extensional faulting, with volcanic alert levels unchanged. One offshore along one of the fastest converging subduction zones on the planet, doing what it always does. Neither points to an imminent catastrophe. Both are reminders that this country is built on some of the most restless ground on Earth, and the faults with the real power to change New Zealand's history are the two that made no noise at all this week. That's the lesson worth carrying out of this video. The earthquake that wakes you up is rarely the one that should concern you most. The most dangerous forces on this planet are almost always the quiet ones, the ones patiently loading, year after year, while everyone's attention is somewhere else. Understanding which fault shook you and which fault could someday break you are two entirely different questions. And confusing them is how a moderate earthquake turns into an internet doomsday story overnight. Knowledge doesn't remove the risk. Nothing removes the risk. But it decides whether you meet it prepared or terrified, and that difference is everything. The ground under Taumarunui will settle. The aftershocks will fade. The headlines will move on within days, as they always do. But 16 kilometers beneath the seafloor off the east coast, the Pacific plate is still sliding downward, millimeter by millimeter, exactly as it has for millions of years. And beneath the South Island, a fault that has kept a 300-year rhythm for thousands of years is already overdue. Nothing about this week changed that. Nothing about this week accelerated it. But it did something valuable anyway. It reminded an entire country to look down and to remember what they're standing on. If you want to keep following this with real seismic data instead of recycled panic, subscribe and turn on notifications, because this region is worth watching properly, and I'll bring you the numbers the moment they change. Thanks for watching. I'll see you in the next one, the next